But that's better. Okay, to begin. So where we ended yesterday was we'd gotten as far as describing the anatomy of the myelinated axon. And then we had begun to describe how the myelination, beneath the myelination, because the myelination is so thick, there's a terrible capacitance in that region. The internodal region just doesn't separate charge very well. But that's an advantage in the system, because what it means is that the ions coming through the membrane at the coming through the membrane at the nodes of Ranvier can now apply their electromagnetic fields almost directly to the next node without needing to depolarize or compensate for the charges along the membrane, because the myelination has now made it so that there are few charges in that region. So we'll walk our way through that. We'll draw that and talk about it in some detail. And then what we'll do is then we'll talk about generator potentials, and we'll go from generator potentials to action potentials. This will be the first indication of taking this information that we've been talking about to produce an action potential and propagating an action potential, and how we're going to take that information from the tip of our finger, an example of a particular kind of sensory input, touch basically, and propagate that information into the central nervous system. Now there's going to be a couple step event here. The first thing we're going to do is we're going to set up a generator potential. The generator potential is going to be produced by the opening of stretch-activated channels. Basically, we'll pull on the membrane, that's going to open channels, and ions are going to come in. Now, unlike the voltage-gated channels where we have an all-or-nothing response, either we reach threshold or we don't, in this particular set of cases, in this particular case, the more we pull on the membrane, the more of these stretch-activated channels we open, the larger the depolarization. So we can say that the depolarization or amplitude of the generator potential, just reflecting the number of positive ions that are coming in, the amplitude of that potential is proportional to the strength of the stimulus. Now if you get down into the weeds of it, it's actually a log function, but for our purposes, we can simply say the stronger the stimulus, the more ions are coming in. The more ions that are coming in, the higher the probability that we'll bring the membrane at the trigger zone to threshold and fire an action potential. And so what we're going to do here is the first step is to polarize the membrane to a generator potential, and the second step is going to use that positive charge in the generator potential to swing open the gates on the voltage-gated sodium channels to initiate the action potential at the trigger zone to now propagate those action potentials over long distances. So this is the only change we'll make here, is that we're beginning to recognize how we're going to set up those action potentials initially. But then we have to ask a question. And the question is, how do we manage to use this all or nothing invariant signal of an action potential? How do we use that kind of signal to encode information? Because that's, after all, that's what we're trying to do in the nervous system. We're trying to encode information in some way. And we're trying to send that information, encoded as action potentials, to the next cell. And fundamentally what we're going to do is we're going to see that we're encoding information in action potentials by the number and frequency of the action potentials. Basically, once the membrane potential is above threshold, in many cases, it can remain above threshold for long periods of time and continue to fire action potentials. And since we're continuing to fire action potentials, then those signals are heading down the axon. Now, these action potentials occur in a kind of, if you put your phone away to appreciate it, these action potentials now are occurring in a series, and there's a question of how long the series is going to last. And so this information is going to be coded both by the number of action potentials in the series and the duration of the series. Now, basically, that, and we'll draw this, but what's happening is that the action potentials are propagating down to the synapse, the output region of the neuron. And at the output region of the neuron, we're going to see that the neurotransmitter is being released to affect the next cell. Synapses have a long history, and I want to give you some story of where this all came from. It originated in the early 20th century, talking about synapses being a place to clasp or hold. We'll talk about the idea of a receptor substance, and then we'll talk about the crucial experiments that showed that neurotransmitters were chemicals. And then we'll talk about synaptic structure and what the components of the synapse are. We'll talk about the presynaptic element first and the postsynaptic element, and how the presynaptic element transmitter and the postsynaptic element will respond. And the response will be dependent upon how the neurotransmitter binds to ligand-gated channels and opens the channels. But let's start here. Let's start with a couple of figures and summarizing where we were last time. This first image is one that's more detailed than I'll ever ask you to know, but it's worth looking at. And what it's showing is a formalization of the description that we had on the board, the formalization of the description we had on the board at the beginning of yesterday's discussion. And what it's showing is the decay of the potential over distance. Now, it's true that the decay of it over distance of the amplitude of the potential is logarithmic, but that's a detail. What we're trying to say with this figure is that if we apply positive charge at this point, that positive charge now is going to leak out of the membrane over distance. Now, they show this differently for a small unmyelinated axon and a myelinated axon. That's not important for our purposes. What's important is that when you put charge in at one place on the membrane, because of the potassium leak channels, that potential, that charge, is going to leave the membrane, leave the cell across the membrane. So the potential is going to get smaller and smaller with distance. And that's shown here. The potential is getting smaller and smaller within a matter of a few millimeters. So that told us that we needed to have some kind of mechanism to regenerate the action potential. How do we regenerate the action potential and keep it moving along the membrane? And that regeneration occurs primarily by having the voltage-gated sodium and potassium channels lined up along the membrane, basically cheek to jowl. And that's what this figure is trying to show. And what it's trying to show is that we start back here at this point where we have red. We've now flipped the polarity on the membrane. Sodium's come in, and it's changed the polarity from -70 to +40. But because we're sequentially opening the voltage-gated sodium channels, we're propagating this potential along the membrane by sequentially opening those voltage-gated sodium channels, allowing sodium to come in. Now, this shows a detail that I didn't talk about yesterday. I touched on it when we showed that figure of the action potential. But there's a part of this figure that shows the refractory period. The refractory period is the region of the membrane after an action potential has passed where we can't really start another action potential, at least not for some time. And you know the reasons for that. If you think about what we were talking about yesterday, what's going on in this refractory period is that the sodium channels are in an inactivated state. They're closed. And what's more is there's a high potassium permeability, so it's driving the membrane potential away from the threshold and holding the membrane potential at the resting membrane potential or near EK. So that's why we have this region behind the action potential where it's difficult to fire action potentials. And that's the reason the action potential propagates only in one direction. But fundamentally, what the figure is showing is this regenerative ability to sequentially open voltage-gated channels and roll that action potential along the membrane. The problem is that we only can get conduction velocities with unmyelinated axons up around 0.1 meter per second. And we know that that's way too slow for biological function, at least in mammals. And so we need to postulate a mechanism to increase the rate of propagation. And that mechanism for increasing the rate of propagation is largely due to this idea of myelination. And this is a figure that we basically drew in the board yesterday, where we had the plasma we had the neuron, we had the open plasma membrane at sites called nodes of Ranvier, and then we had these internodal regions that were ensheathed or enshrouded by wrap after wrap of the myelin. Now, you remember when we talked about the membrane, we said that, if you put your phone away, I'd appreciate it. When we talked about the membrane at the nodes, we said that there's a high capacitance in this region because the naked membrane is facing the outside world. And that naked membrane is only about 6 to 7 nanometers thick. So it's a really good capacitor. But if you imagine all those charges across the membrane here, the separation of charge between the inside of the membrane and the outside of the membrane is a long distance. We've packed all this myelin around. So where this distance is about 6 to 7 nanometers, this may be a few micrometers. So we've increased the distance by maybe 1,000-fold. Now, what you have to envision in your mind's eye is that when those ions are close to one another, because they're opposite charge, they're going to draw themselves close together, and they're going to hold themselves one to the next. But then, as we separate those charges farther and farther apart, the influence of one charge and the other gets less and less and less. And so what's happening is in this region, the charge is far apart. So this has very little capacitance in this region. Because there's little capacitance in this region, what we see is that the charge that comes in at the membrane here and has the electromagnetic field has very few charges in this internodal region to discharge or offset. So that means the charge coming in at the node can almost immediately go to the next node and depolarize the next node. There just isn't all that pesky capacitance in here taking up the energy of the ions coming in at the nodes. So let's draw that and extend that a little bit more. So the questions about that? Yes? I'm sorry, I missed all that. It acts as an insulator. So the myelin acts as an insulator, but more important than acting as an insulator so the ions can't move, it's separating them by a long distance. And you can get a sense of this if you take two poles of you take two magnets, where you can either use the opposite poles or the same poles. But if you use opposite poles, you get closer and closer and closer, they'll pull themselves together. But that falls off as a square of the distance. So the farther they are apart, the less interaction they have. And you can think of each of those ions as being like a little magnet. So when you separate them by that far, they can't interact with one another. And it's that interaction, the electromagnetic field's interaction across the phospholipid bilayer, which causes the high capacitance of the phospholipid bilayer of the membrane. But now you have wrap after wrap after wrap, so they're far apart, they can't interact. So there aren't many charges along that membrane. The energy of the ion can't interact, the negative ions on the inside can't interact with the energy of the positive ion on the outside because they're just too far away. Sure. Yeah.
Between the plasma membrane, does that slow down the movement of the electromagnetic field?
So let me speak to that. I will speak to that when I draw this on the board. Okay. So let's draw that and think about it. So quickly, this is the membrane. That's the continuous membrane. You remember from yesterday that if we just had continuous membrane, those charges would be stacked up right along the membrane. But in a myelinated axon, we have these layers of myelin. And I'm just putting a few of them in here, but there could be hundreds of them. And effectively, because we have all of these layers of myelin, we've generated a terrible capacitor. Because the distances are so great, we're at the, try it again, here at the node of Ranvier, and this is to answer the question that just happened. Here at the node of Ranvier, there will be negative charges on the inside and positive charges on the outside. This is naked membrane, so it's a pretty good capacitor. But there may be, a tiny fraction, maybe 0.1%, as many charges along the membrane here. Now remember, we said that the nodes are where we're going to have the voltage-gated sodium channels, and their counterparts, the voltage-gated potassium channels. I won't draw all of them in, but I think you'll recognize where we're headed here. That when there's a perturbation in the system, and we turn this negative charge into positive charge, we now begin to open the gates in the sodium channels and in comes sodium. we'll have millions of these sodium ions coming in at this site. And each one of them will carry with it a slight electromagnetic field. The electromagnetic field is capable of discharging the capacitor on this membrane, but there just aren't many charges in this region. There just aren't many charges in this region so that this energy doesn't have to be used to discharge the capacitor. And instead, the energy can go directly to the next node, where I have these voltage-gated sodium channels. So now the electromagnetic fields can go directly to this node without really having much effort expended in discharging the capacitance, and begin immediately to open these channels. Now they will also have to discharge the capacitance at this site. That's true, but these sites are tiny compared to the long distances that are ensheathed by myelin. So there just isn't much capacitance in here, and almost immediately this goes to the next node and discharges that node. There was a question back here.
So like, almost like when it's just like the plasma membrane, is it like that, like positive charge has to balance that charge outside the plasma membrane?
No, this is the charge on the inside of the membrane.
Okay.
So what it has to do is it has to negate or offset the charge on the inside of the membrane. So that we can then begin, as we said yesterday, that then will allow for the opening the voltage-gated channel, so we can subsequently allow ions to move through the voltage-gated channels. Okay? Yes?
What is
I told what a capacitor was yesterday. Go back and look at your notes. Yes?
So are the potassium leak channels also clustered in the nodes of Ranvier?
The potassium leak channels. Well, yes, they're clustered at the nodes of Ranvier, and I showed them here. In reality, they're clustered underneath the membrane. And the reason for that is that, this is a real detail. When the potassium starts to flow out, particularly if you imagine in this region where you're between the two great mounds of myelin, when the potassium goes out, if we just had them here at the nodes, we'd actually start to build up potassium concentration in here. And it wouldn't take very much potassium before we started to polarize the membrane at this site, because an increase of potassium in the outside, if you look at the Nernst potential, will cause this membrane to depolarize. That would then kick the sodium channels into the inactivated state. So what we do is we walk around that problem by putting the voltage-gated potassium channels underneath the myelin. And now the potassium can be pumped out and put into these oligodendrocytes, moved from loop to loop here and out to the outside world, avoiding the problem of increasing the concentration in this confined volume. Okay. Anything else? Yes? I'm sorry, both of you. You first, then you. So, and farther back. No, you.
So you're saying the voltage-gated potassiums are underneath the inner node regions, but then the leak channels are in the open of the nodes of Ranvier?
The leak channels will be mostly in the nodes of Ranvier. There are probably some underneath the myelin too. There are a few potassium channels underneath the myelin, but they're mostly right at the edges here underneath the myelin. And I haven't drawn it very well, but right at the edge of the node of Ranvier, there are these sort of open loops, because remember, we've wrapped the myelin around and around, and there'll be open loops of cytoplasm for the oligodendrocytes. And we think that there are gap junctions between the different membranes of the oligodendrocyte in this region, and the potassium is passing through the cytoplasm through gap junctions till it gets to the outside world. You had a question?
So the sodium the electromagnetic field goes to the next node of Ranvier, and that electromagnetic field triggers the voltage-gated sodium channels to open and let in more sodium.
Yes, exactly.
And those sodium that come in go to the next one.
Exactly. So what she's saying is we have a sort of a cascading event where the sodium comes in at this site, moves almost, the electromagnetic fields can now move through the conducting medium of the cytoplasm, move to the next node, open these, sodium comes in. These then go to the next node. And so now then we can rapidly propagate these potentials. So where the unmyelinated axon is propagating per second, this is working at about 110 meters per second. Yes?
When sodium comes down into the ligand-gated channels, does that also produce an electromagnetic field?
Let's hold off on that, but I'll answer it quickly. Yes, when the sodium comes in through ligand-gated channels, it will generate an electromagnetic field. And just like this, the electromagnetic field will be propagated through the cytoplasm. But in the input region where we have the ligand-gated channels, we don't have voltage-gated channels to regenerate it. We have to take that potential all the way to the initial segment or the trigger zone, which is right next door to the cell body. So we have to propagate those potentials over some distance, and we'll come to that probably. I'd like to do it today, but it's probably going to be Monday. Anything else? Yes?
With the notes about how like it moves 110 meters per second because like with the myelinated regions like what can I say like there doesn't have to be any energy to like offset those charges, so like all the energy can just be used to.
Right. So the question is, where's the energy dissipated? Well, the energy is not dissipated by offsetting many of these charges in the internodal region. So the energy now can be conducted through the axoplasm to the next node and expended here first to discharge the capacitance. But this is a small area of membrane, so it doesn't take that much to discharge the capacitance here, which then opens the voltage-gated channels. And off we go. And we just do it over and over again. In this way, by iteratively opening these channels, we can propagate the potential at 110 meters per second. So that's basically the story of how we send signals. But let's now bring some ideas together and begin talking about a generator potential. A generator potential in the input region of a sensory neuron. Okay, so let's imagine that my hand is out here. And this is my thumb and 4 fingers. That's a hand as best I can do it. And out here we're going to put an input region of a touch sensitive neuron. So you can imagine one of these touch-sensitive neurons at the tip of your finger. You can imagine reaching out and touching something, and that begins the information flow of how you're going to take that information to the brain. But it's a several-step process. The first step here, if we look at these neurons, I take this neuron and blow it up here. And I'm going to label this as the input region of the sensory neuron. In the input region of the sensory neuron, there are these channels. I'm going to put them in orange. And they're gated. They're said to be stretch activated channels. So they're not dependent upon voltage, they're not dependent upon neurotransmitter, they're just dependent on tugging on the membrane. So you can imagine you're down at the membrane level and you start to pull on that membrane. By pulling on that membrane, you literally open the channels. The characteristics of this inside of the membrane are the same as we've seen before. That is, it's negative on the inside. And when these channels open, these channels are permeable to sodium. So we're down around the resting membrane potential, down around the equilibrium potential for potassium, the driving forces on sodium. So we pull on the membrane, and sodium comes in. Now, one of the characteristics that separates this kind of channel from the voltage-gated channel is that, I'll put it down here, the number of stretch-activated channels that open is proportional to the strength of the stimulus. Another way of saying this is the more we pull on this membrane, the more channels we open, the more sodium comes in, the greater the amplitude, the greater the number of charges, the greater the amplitude of the potential at this site. But all along the membrane, whether this is unmyelinated or myelinated, will be potassium leak channels. So that means that the potential that we set up here can't propagate very far before it leaks out of the membrane. So that means then that we need to regenerate the potential. We're going to have channels in here, which will be the voltage-gated sodium channels. They'll, of course, be accompanied by their counterparts, the voltage-gated potassium channels, but I won't draw as many of those in. We can imagine these were all on the membrane if we're unmyelinated, but we can also, just as easily, say that we have this myelination. Now, this site here, where we cluster the voltage-gated channels, has a name. This site where we cluster the voltage-gated channels is called the trigger zone. And it's called the trigger zone because it's the site at which we're going to trigger the action potential. There's nothing different here than what we've talked about before. We simply cluster the voltage-gated channels to the site. We're using the positive charge that has come into the cell through the stretch-activated channels. That positive charge now is being delivered, the electromagnetic fields of that sodium is being delivered to the voltage-gated channels, the trigger zone. They open, in comes sodium, and then from node to node, we can propagate the potential just as we talked about in the upper panel. So that's how we initiate that potential and get it to propagate to long distances. Yes?
So the action potential in neuron is an all or nothing event. What is the significance of the proportional stretch activated channel opening?
Okay, so the question here is, what is the distinction between this so-called, let me label this as a graded potential, the graded potential is said to be graded with the strength of the stimulus. That's just a different way of saying that the number of sodium ions that are going to come in is proportional to how much we pull on the membrane and the number of channels we open. But we're using this as the first step, the sodium, because we need a way now of charge. We need a way of using charge and transferring charge to the voltage-gated sodium channels to open the voltage-gated sodium channels. So this is the intermediate step. We're opening those channels to let sodium come in. Those electromagnetic fields now can work on these voltage-gated sodium channels, and that starts the opening of the voltage-gated sodium channel. Because there's threshold. Once we get enough positive charge in there, we reach threshold, off the action potential goes. It always goes to plus 40, comes back down again. So it's all or nothing. Either we get to threshold or we don't, and it's stereotyped. It's always the same amplitude and always the same duration. So we're moving from this potential, which is graded with the strength of the stimulus, to one which is all or nothing. And we'll set up those action potentials. Does that help? Not sure. Why is it significant that it's graded? And why is it, okay, so why is it significant that it's graded? There may be times we have just a little bit of a tweak on the membrane, and we don't get enough sodium to come in to get this to threshold. We have to pull in this membrane fairly hard in order to get enough sodium to come in to get this membrane to threshold. This will become even more obvious when we get to ligand-gated channels out on the input region of neurons, where each synapse may only open a few hundred of them. And we get a potential of only a millivolt, but yet we have to get enough positive charge at the trigger zone to polarize the membrane from -70 to about -55. We need 15 millivolts of charge. And here we can get that fairly easily by opening the channels. But the other point here is the more sodium we let in, the greater the depolarization, the greater the probability that the membrane will stay above threshold for long periods of time, so we can fire a whole series of action potentials. There was another question back there, yes?
Could you clarify, is the trigger zone just the mediated sodium channels, or is it that whole
So the trigger zone is the region of the membrane where voltage-gated sodium channels and potassium channels are clustered. It's just as though you can think about it as the first node of Ranvier in a myelinated axon. Or an unmyelinated axon, it's just where we cluster enough of these voltage-gated channels where we can generate an action potential. Yes, and then yes.
Is it kind of like a domino effect? Like as if we get enough energy from like the sodium, then we can like set off the rest of the reaction because they all just like fall on top of each other kind of thing?
It's much like a domino effect. I think the domino effect, which you're explaining, where we get enough energy coming in from the generator potential, starts the dominoes falling, is easier to see in an unmyelinated axon because you can imagine those channels being lined up like dominoes, one next to another, and off they go. It's a little harder to see how it's going to work in a myelinated axon where the dominoes aren't right next to one another. There has to be an action at a distance to start knocking over the dominoes at the next one. Okay? Yes?
Just for a real life example, so with certain maybe like neurodegenerative disorders, are these action potentials going faster, or maybe in people with like disorders like ADHD with that like people are really impulsive, are these things traveling faster in those populations?
So the question here is, can we see differences in behavior based on the rate of propagation of the action potentials? Probably not. The differences in behavior are arising from interactions of neurons in the central nervous system. Thousands and thousands of synaptic potentials deciding what kind of signals to send from one neuron to the next. We're probably not getting much of that at this site. Now, having said that, there are certainly diseases in the central nervous system. We think that chronic traumatic encephalopathy, CTE, may be due to a breakdown in the axons. In that case, you're not propagating action potentials very well. And as we discussed the other day, when you break down the oligodendrocytes in multiple sclerosis, then that's going to have an effect on action potential propagation. There are diseases in the peripheral nervous system that will do that too, called Guillain-Barré syndrome, and they will break down the myelin. It's not as serious as in the central nervous system because we seem to be able to regenerate that myelin more easily in the peripheral nervous system, and those tend not to be, for reasons I don't understand, Guillain-Barré does not seem to be relapsing or remitting.
Where like a lot of people experience paralysis because of the damage, correct?
You can have people experience paralysis out in the peripheral nerves, but you recover pretty well. I knew years ago, I knew a guy who was a competitive fencer at the Air Force Academy, and he got Guillain-Barré syndrome, and he demyelinated all his peripheral nerves. But within about 6 months, he was back fencing again, and so he remyelinated and did just fine. And it seems to be permanent. Once you've had that, you may get some deficits, but you don't seem to get long-term deficits. Yes.
So I understand that stretch activated channels are opened by stretching them. What is stretching them apart?
Oh,
Is it something binding, or?
just stick your finger out. Push on something. There it is. Yes.
So when the stretch activated channels open, but they don't let in enough sodium to reach the threshold, does the membrane go back to like -70 until it gets more, or does the sodium hang out that like a higher?
So the question here is, if we don't get enough sodium coming in, here to generate a generated potential to reach threshold, what happens to that positive charge? It leaks back out through the potassium leak channels. We have potassium leak channels everywhere. We can't set up a membrane potential without potassium leak channels.
So would you have like potassium leak channels like right next to the stretch activated sodium channels?
Yes, you would have potassium leak channels right next to the stretch activated channels. It's just you're going to get a whale of a lot more of the stretch activated channels than you have the leak channels. And the leak channels are fixed in number, and they're not gated. So once you start pulling on the membrane, you can now have so many more sodium channels open that you can offset that leak current, those leak channels, and depolarize the membrane. Okay?
Are those leak channels, like, is there a set number for like each neuron or like each neuron?
I don't know that there's a set number. I don't know that. I suspect there's a range, and perhaps some neurons are more sensitive than others dependent upon the range of those channels. I don't know. Okay, we need to move on. So what I want to do is I want to get this information back into the central nervous system. And so now let's imagine, we go from the hand, we can imagine this neuron is a single neuron. It goes all the way back, and now I'm going to put a cell body on it. So this is the cell body of the primary sensory afferent. This is all the periphery, but we're going to have to send this information to the central nervous system. We're going to talk about this a little more next week, but here's the spinal cord. There's a cross-section of the spinal cord. There's always a butterfly arrangement in the spinal cord. This is called the gray matter. This neuron is going to send a process. It's going to be one continuous process that goes into the central nervous system. We're going to see a little later that this neuronal cell body is going to be in a region called the dorsal, or more commonly these days, posterior root ganglion. And the action potentials which are set up here are going to propagate all on this membrane, propagate into the central nervous system, and someplace here in the central nervous system, that neuron is going to synapse onto another neuron. This is going to be an excitatory interneuron. And in some cases, this excitatory interneuron will synapse directly onto a lower motor neuron. This is going to be a lower motor neuron. And the lower motor neuron now will go out and innervate muscles in the hand. So that in this case, you can reach out and touch something, and then you can move your hand in response to that movement. Now, that voluntary movement's going to have to take information up to the central nervous system. But this brings us to the idea of how we have a primary sensory afferent communicating to the next cell, in this case, an interneuron, and the interneuron communicating to the motor neuron. And what we want to think about now is this communication, because this is going to be communication at a site called a synapse. So what I want to do, what I want to think about now is how do we relate the action potentials generated out here, these all or nothing, stereotyped or invariant signals, how do we relate that to the amount of neurotransmitters being released to the site? How do we encode that information? So over here, I want to bring up the idea of frequency coding. using action potentials. I'll remind you that whenever we have an action potential, it starts out about minus 70 millivolts. And if it reaches threshold at, more or less minus 55, it has that very rapid depolarization to about plus 40 millivolts and a repolarization back down again. They always look the same. They're always the same amplitude. They're always the same duration. So normally, the way we teach this is we imagine generating one action potential down here at the trigger zone. The action potential propagates along the membrane, reaches the output region of the sensory neuron, it releases neurotransmitter. But in reality, it doesn't work exactly like that. What we do is we use series of action potentials. And the way we encode the information, basically, in terms of how much neurotransmitter we're going to release, is the number of action potentials in a series or sequence. So we can imagine here, if we, let me make this a little smaller so I can get it in, start out minus 70, fire an action potential. And as long as we've depolarized the membrane above threshold, these action potentials can continue to fire. So rather than having a single action potentials, we have having a single action potential, we have a series of action potentials. The frequency of the action potentials in the series will determine how much charge is arriving at the output region. That will then determine, through a series of events, the amount of neurotransmitter that's released. If we have action potentials which are coming, the time between each action potential is longer, so we have fewer in the series, then we have less charge arriving at this site, releasing less neurotransmitter. The other issue here is not only the frequency of action potentials, but how long the series lasts. So if you have a short bout here, if you only have a few action potentials, then you're not delivering much charge, so you're not delivering much releasing much more transmitter. If you have long bouts, and this is going on for a long period of time, then you release lots of neurotransmitter. So that's the way we encode information in the nervous system. So we take these all or nothing signals, and by using this frequency coding, we can determine how much neurotransmitter are going to be released, will be released to the synapse. But let's now think a little bit about what we mean by a synapse. And let me work our way through some of this on the backboard. We can actually ask, what is a synapse? And this was a question that was asked in the early part of the 20th century, was asked almost immediately after Cajal went around Europe and gave his lectures on the neuron doctrine. And never remember names, I'm not worried about names, but I need names to tell the story. There was a guy in England called Sherrington. And he was a physiologist at Cambridge. And Sherrington went to the seminars that Cajal had given, and he said, well, if there are individual units called neurons in the nervous system, there must be a place where the neurons communicate with one another. And he imagined a place where two neurons would come close to one another, and then would kind of hold on to one another. He didn't know how they'd communicate. He didn't know what mechanism they would use to communicate, but he imagined the two neurons holding on to one another. And so he coined the term synapse. It means to clasp or hold. Now, this brought up an argument because Sherrington couldn't tell you how that communication was going on. And so it brought up an argument. One argument was said to be soups, and the other argument was said to be sparks. Soups said that there is chemical communication between neurons. Spark said, no, 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 it's not chemical, it's electrical continuity. There's some sort of mechanism where a spark could move from one cell to the next. This turns out pretty much not to be true, although there are gap junctions. This is predominant thinking that we have now, and it took years to settle it. And I want to spend a little bit of time talking about how this Soup's argument was developed. Again, don't remember the names. There's a guy named Langley. And Langley was a pharmacologist. Where Sherrington was a physiologist, Langley, also working at Cambridge, was a pharmacologist, and he knew a lot about plant alkaloids. He was interested in how plant alkaloids would interact with nervous systems. And he recognized that he could use nicotine to change the activity of nervous systems. And so he did an experiment. He took some nicotine and he put it in solution in a beaker. And then he took a mouse, killed a mouse, dissected out a muscle, and dissected that muscle over and over again until he had a single muscle fiber. So this is meant to be a single muscle fiber. He could see that there was a site where the neuron came down and came close to the muscle. He called this an end plate. And then he did just, I think, a brilliant experiment. He took a brush, a camel's hair brush, a very fine camel's hair brush, teased out all of the fibers in the camel's hair brush until he was down to one. He then dipped the brush into the nicotine and started walking, basically, with his brush, looking under the microscope. He would walk along the membrane of the mouse cell, and nothing would happen, and nothing would happen, and nothing would happen, and then he would get close to the end plate, and nicotine caused contraction. Let me finish this idea and I'll let you go. What he said from this is there's something in the cell, there's something at the end plate, which is a receptive substance. Now, the problem with this is nicotine. It's a plant alkaloid. It doesn't tell us very much about what's going on in the nervous system, but at least it said there's some receptive substance at the end plate that caused the muscle to contract. It was another 20 years, or at least 15, before what the receptive substance was and what the neurotransmitter was. And we'll start there on Monday.